All right, so the next topic probably comes about 3 days later than you want it to, because this is the pH of salts topic. And so you probably just did this lab experiment, right, this week. And from what I understand, that is one of the harder experiments that you'll do. So my apologies for the mismatch here in timing. But we're going to now start taking a look at the relationship between acid dissociation constants and base dissociation constants for conjugate acid-base pairs. So this is the one big thing here to remember when we're looking at this relationship, is that it only works for conjugate acid-base pairs. Okay. So let's think back to our equilibrium chapter, where we take a couple of equilibria and we want to add those equilibria together to come up with some sort of overall chemical equilibrium. And you recall that what we'll do is multiply the K values together to get the overall K for these summed equations, right? So let's say we put a conjugate acid-base pair in solution in the same beaker together, okay? And we want to find the overall K associated with that. So we have our two equilibria at play. We have our weak acid and its equilibrium with water, so it's going to form H3O plus and A minus, the conjugate base. But we're also going to somehow, probably in the form of a salt, put the conjugate base in solution. So this is different. I mean, it's the same function, the same formula as this A minus, but it's a different way of adding it to the solution. Okay. So we're going to explicitly add A minus to the solution. It's going to have an equilibrium with water to form the conjugate acid and hydroxide. So what happens when you add these two equations together? So take a minute there and write that out. I'll do it with you. So what you'll find is that HA appears on the reactant side of the first equation and on the product side of the second equation, so those cancel. A minus appears on the product side of the first equation, the reactant side of the second, and those cancel. And so what we're left with is 2H2O in equilibrium with H3O plus OH minus. This is our special water equilibrium, and we know that has a Kw associated with it, correct? And Kw is equal to, and you can see from this equation, the concentration of H3O plus times the concentration of OH minus. And so what that tells us is that Ka times Kb is equal to Kw for conjugate acid-base pairs. And that's going to be important because sometimes you're going to need a Ka value or a Kb value, and usually you can find those in a table, but sometimes you can't. So if you look up the Ka value for acetic acid, that's relatively easy to find. But to try to find the Kb value for the conjugate base for acetate ion, you usually don't find it in a table. Maybe probably do now. Historical, when we had an actual book that had Ka and Kb values, we couldn't put everything in there. But we have this relationship. And so if you have a Ka, you need a Kb, you can use Ka times Kb equals Kw, and solve for the variable that you need. And if we take this one step further, recall that pKa is going to be minus the log of the Ka. Maybe we didn't see this yet, actually, but taking minus the log of something is what we do for P. So pKa is equal to minus the log of Ka. pKb is minus the log of Kb. If we have Kw equals Ka times Kb, and we take minus the log of both sides, so we'll have minus the log of Kw equals minus the log of Ka plus minus the log of Kb. This part coming from the rule for logs, if you multiply things together, it's the same as taking minus the log of the individual thing and adding them. What we'll end up with is pKw equals pKa plus pKb. And this is a useful equation too, because sometimes we're given pKa values. You're going to see pKa a lot if you take organic chemistry. Okay. The other convenient thing is that we know that at 25 degrees Celsius, Kw is equal to 1 times 10 to the minus 14. And so pKw then is equal to 14. So 14 is equal to pKa plus pKb at 25 degrees C. So 2 other equations here for your toolkit, I guess. 14 equals pKa plus pKb, and Kw equals Ka times Kb. So add these to your list of equations. Minus the log of H plus equals pH. Minus the log of OH minus equals POH. pH plus POH equals 14. All of those, okay? So make sure you're able to manipulate these expressions to use them fluently. And again, the Ka times Kb is only for conjugate acid-base pairs. That's important. Questions on this? All right. So let's look at a couple questions here. Phenol, which is a weak acid, has a Ka of 1.3 times 10 to the minus 10. Is it a stronger or weaker acid than water at 25 degrees Celsius? So the information that you have is the Ka value. So we really just need to compare the Ka value with the Kw to solve this problem. So our Kw is effectively a Ka. So considering water as an acid, how much H3O plus is formed. Kw is special because water forms both H3O plus and OH minus. That's why it's sort of designated that way. But if we compare the Ka value for phenol to the Kw for water, the larger value is going to indicate a stronger acid, because that suggests there's more dissociation, more products formed, right? This goes back to our equilibrium chapter. Larger K, more products formed. Okay. So if we compare the phenol Ka to Kw, Kw is 1 times 10 to the minus 14 at 25C. Phenol is 1.3 times 10 to the minus 10. So phenol having the larger value of K is a stronger acid than water. Make sense? So no calculations needed here. Let's compare hypochlorous acid, which is HOCl. So not a strong acid. And you can tell because we have a Ka for it, right? The Ka for hypochlorous acid is 3 times 10 to the minus 8. Is phenol stronger or weaker than hypochlorous acid? Weaker, yep. So phenol has a smaller value of Ka than hypochlorous, so so phenol is a weaker acid. Hypochlorous acid is the stronger acid. Everyone okay with that? Okay, so let's move on and think about now which of these will have a stronger conjugate base. Okay? Does phenol have a stronger conjugate base, or does hypochlorous acid have a stronger conjugate base? So what values do we need to compare to answer this question? Kb, yes. And so how are we going to find Kb's? Kw equals Ka times Kb. And we have the Ka values for phenol and hypochlorous acid. So let's just sort of make this as obvious as we can, I suppose. We have both weak acids. We're going to just call it general now weak acid HA plus H2O in equilibrium with its conjugate base and H3O plus. We are now concerned about the equilibrium with A minus and water, and how it forms OH minus and HA. So this second equilibrium is what we're considering when we are looking at a Kb value. So A minus in this case is a base. We're looking at how it forms hydroxide and HA, conjugate acid. So when we compare our Kb's, the larger value of Kb is going to be the stronger base, more products formed. Right? Let's see, what should I do first? Hypochlorous acid, our Ka is 3 times 10 to the minus 8. Kb is equal to Kw over Ka. So that's 1 times 10 to the minus 14 over 3 times 10 to the minus 8. And I get 3.3 times 10 to the minus 7. So this is for, OCl minus, so the conjugate base of hypochlorous acid. For the conjugate base of phenol, we end up with a Kb of 7.6 times 10 to the minus 5. So which is stronger? Conjugate base of phenol, right? Did we need to do the calculation? Not really, no. We can look at our Ka values, okay? The smaller Ka is going to have a stronger conjugate base. It's just because of the way that mathematically works out, right? And so really you could take a look at Ka values and be able to predict the strength of the base for basically the reverse reaction. Okay? Make sense? Yes.
To clarify, you said smaller Kb has the stronger conjugate base?
The smaller Ka, okay, so if you're looking at Kas, say we didn't want to do any calculations, the smaller Ka, the acid with the smaller Ka, let me write it out. Acid with smaller Ka makes a stronger base. So in this case, phenol had a smaller Ka than hypochlorous acid. It makes a stronger conjugate base, yes.
So weaker acids make stronger bases?
Weaker acids make stronger bases, yes. Yeah. Yes, good work. Other questions, thoughts? Okay, cool. All right. So now that we've sort of established our Ka-Kb relationship, let's start taking a look at salt solutions. I do think that determining pHs of salt solutions is one of the harder things you're going to do this semester. Not only do you have to remember ions that go into making salts, you have to remember how those salts break apart in solution. You have to be able to imagine what possible products are going to be formed when these ions react with water. And then, even on top of that, we are occasionally going to ask you to calculate the pH of a salt solution. And so there's just a lot that goes into this. Now, I will recommend writing out equilibrium, writing out dissociation, because I think that is incredibly helpful to sort of keep you on track and help you see what is happening. And we're going to work through some examples, and I'll show you what I mean. But first, I want you to, and let's ignore this slide a little bit. Before we get to what's on this slide, we're going to test your recall. Make a list of the strong acids in the box where we're going to put the conjugates, and make a list of the strong bases in the list where we're going to put the conjugate bases. Feel free to work with your neighbor.
I've got HCl, HI, HBr, HClO3. Yeah, that's a good one. HClO4, H2SO4, only that first proton, and HNO3. Did I miss any? Hope not. And then strong bases, we have lithium hydroxide, LiOH, sodium hydroxide, NaOH, potassium hydroxide, KOH, rubidium hydroxide, RbOH, cesium hydroxide, CSOH, calcium, strontium, and barium hydroxide, which all have 2 hydroxides per. Calcium, strontium, barium. Okay. Yeah, that's totally what that is. Okay, so now in the box on the left, let's write the conjugate bases of these strong acids. So basically, we're just going to let these dissociate. We're going to ignore H+, right? So our conjugate bases are going to be Cl-, I-, Br-, ClO3-, ClO4-, HSO4-. Watch that one, because that second deprotonation, that is a weak acid. So this is the conjugate base, and it only differs by 1 proton from H2SO4. And then NO3-. For the strong bases, we'll write our conjugate acids. So again, basically allowing these to dissociate. They all dissociate completely, even the ones with 2 hydroxide. And so we're going to be looking at the cations. So we have lithium ion, sodium ion, potassium ion, rubidium ion, cesium ion, calcium ion, 2+. Strontium 2+, and barium 2+. Why are we writing all of this out? When you have, oh yes, sorry.
So for like the calcium and then OH2, you take off both of them?
You take both of them off, yeah. Because of the structure, because when we put that in solution, it completely dissociates. That's a little different than the H2SO4 situation. Okay, so when we have salts that contain any of these ions, okay, none of these ions affect the pH of the solution. So if you can recognize these ions in the salt, you know that none of those are going to alter the pH. You put sodium chloride in solution at pH 7, it stays pH 7 after sodium chloride dissolves. Okay. What other ones did you do in lab this week? Calcium chloride? Name is neutral. You did a billion of them. Probably a bunch of nitrates, those dissolve really well. Okay, so the main idea here is I want you to be able to recognize these ions, okay? And then recognize that these ions do not affect the pH of the solution. Now, you don't necessarily have to memorize all of these. There's a procedure that you can go through to see if they would affect the pH of the solution. Okay?
So basically when we say, for instance, does chloride affect the pH of the solution, we're essentially saying, does chloride ion react with water? And this is sort of a thought exercise that can be a very tricky step. Okay? So when we're thinking about whether chloride can react with water, we have, again, chloride ion is an anion. The only way that the chloride could react with water is if it reacts with H+. It will not react with another anion, OH-. Okay? So when we react things with water, we're basically saying, will an anion react with H+? Or will a cation react with OH-? That's what we're basically getting this all down to. Will an anion react with H+? Will a cation react with OH-? Now, you might be thinking that's going to be really hard to predict, but it's not too bad because we know our list of strong acids and strong bases. Okay? So let's see if we react our chloride ion with water. So we're imagining the chloride ion is going to react with H+. If that were to happen, it would form HCl, right? But what do we know about HCl? It's a strong acid, completely dissociates in solution, and so that reaction will not occur, okay? So if you end up with, when you're reacting an anion with H+, if you end up with a strong acid, the reaction doesn't happen. Those acids don't recombine in solution. That by definition. Everyone okay with that? Did you have a question? Happy to answer.
Just to clarify, like the answer is no, right?
Oh, does the Cl- react with water? The answer is no, right? No. Yeah. Okay, but it gets a little bit more complicated when we have the conjugate base of a weak acid. Right? So here we have a salt, sodium acetate. If you like salt and vinegar chips, you probably like sodium acetate. That's what they put on there. Sodium acetate is a salt, right? Notice what I've done here. I've taken the sodium acetate, I've written the dissociation, okay? And this is a step I want you to do. I formed sodium ion and acetate ion, and we're using a single arrow because the sodium salt completely dissociates in water.
Just to clarify, for like the last slide. Yeah.
You want me to just go back?
Yeah.
Okay. So we've written our dissolution for sodium acetate. Again, all sodium salts are soluble. So you have to go back to whatever chapter that was and remember your solubility rules. We'll get to that even more, actually. In this chapter, you're going to see soluble salts. Okay. So we have our sodium acetate. Okay. So what do we do next? Let me just figure out where we are on the slide again. So we've made a solution of sodium acetate. We've completely dissociated the acetate and the sodium from the salt. And now we're left with sodium ion and acetate ion. Acetate ion is the conjugate base of acetic acid, right? So that's a weak acid. Now we have our anion, right? We want to see will it react with H+. So essentially what we're saying is if we take our acetate C2H3O2 minus and water, will we form HC2H3O2 minus and then OH minus? And the OH minus is coming from the water. So we've taken one of the protons from H2O, reacted it with the acetate ion, and we're left with OH minus. Oh, hang on. We need to erase this minus sign. So does that reaction happen? Yes, it does. The reason we know that is that this is not a strong acid. So this is an equilibrium that can happen. So this reaction, RXN, occurs. We can tell because a weak acid is formed. Okay, so what would the pH of that resulting solution be? We put acetate ion in water. What pH is going to be, acidic or basic? It's basic. Basic. Yeah. It's basic because you end up with OH minus. And that is a stronger base than this is a weak acid. Okay? This is tricky, right? This is like flip-flop in your brain a bunch of times. Yeah.
But from this information, we can figure out pH.
From what we have now,
We need more numbers.
yes, you would need a K and the concentration. Yeah, so the question was, could we figure out a pH from this? You would, in order to solve for a pH, you need the starting concentration and the Ka value. Who designed this stupid one? Okay. Thoughts on that? Questions? Yes.
Would it only be slightly basic since it's a weak acid, or would it be like more significantly basic?
It is not going to be like, well, we could calculate it, but you don't want to do that. Okay. It's not going to be hugely basic, but because you have, we're dependent on the Kp value for this concentration. We will do some of those calculations. I know, hold on, yeah, so excited. Okay. So here we go. Let's keep moving on with this. We have our acetate ion. Can I be lazy? Is that all right with everyone? Shane, you don't get to vote. We're going to just call the acetate ion A minus. Okay? We have A minus. We're going to write out our equilibrium expression. A minus plus water, H2O, in equilibrium with HA plus OH minus. And so for this, our Kb expression, again, Kb because acetate ion is a base, Kb is equal to the concentration of HA times the concentration of OH minus over A minus okay. And then the next thing says to calculate Kb for acetate ion, given that the Ka for acetic acid is 1.7 times 10 to the minus 5. And the other piece of hidden information, which will occasionally be hidden, especially in your homework, is that this is 25 degrees C, and so Kw equals 1 times 10 to the minus 14. Okay? You may not be always given that piece of information. If you're not given that information, you can assume that that's true. So Ka is going to be equal to Kw over Kb, which is 1 times 10 to the minus 14 over 1.7 times 10 to the minus 5. That's our Ka. And we end up with 5.6 times 10 to the minus 10. That is the K. The answer that we got is for Kb. Oh, you're right. Sorry. I messed that up, didn't I? Yeah, I swapped my K for Kb. So you asked about if this is going to be very basic or how basic, basically. So because our Kb value is pretty small, we're not going to get a lot of product form, and so it's not going to be hugely basic. So the other thing, you guys don't have a slide for this, so you might need to make it yours, however your notes work. So we were looking at sodium acetate, right? And we said we put that in solution, we form sodium ion and the acetate ion. These are both aqueous. And we so far have only looked at how the acetate ion affects the pH. We haven't really considered the sodium ion. And I mentioned when we were initially looking at how to determine if anions or cations affect the pH of a solution, that you take a cation and you see how it would react with OH minus, with hydroxide. And that would help you determine if it affects the pH of the solution. So essentially, what we're going to do is take our sodium ion, react it with water. Again, we take our cation, see how it reacts with OH minus, and determine if we could have a reaction that takes place. If we end up with a strong base on the product side, that reaction does not occur. Okay? So if we do sodium ion plus water, we could, in theory, end up with NaOH, because we're seeing how our cation reacts with hydroxide. And then H plus is the other product. Now, we know that NaOH is a strong base. So this reaction doesn't occur. And that means that sodium ion does not affect the pH. Affect or effect? Okay. Oh, it's all on you now. Yes? Can you say that one more time? Oh, so you do both. So whenever you get a salt and you want to determine the pH, you're going to take the anion, see how it could react with H+. You're going to take the cation and see how it's going to react with OH-. And then go through this same process. Do it for both anion and cation. Okay? Does that answer your question? Okay. Yes?
If we end up with both of them reacting, we get a Ka and Kb.
Yes. Beautiful segue. Okay. Let's sort of summarize and then we'll answer that question. Okay, so if we have a salt whose cation does not react to affect the pH, that means it has neutral properties, something like sodium ion, like we just saw, but the anion is the conjugate base of a weak acid, the solution ends up being basic. Okay? So if the anion is the conjugate base of a weak acid, the solution formed will be basic. Okay. I guess we'll get to that segue in a couple more slides. So if we have a salt that contains the conjugate acid of a weak base, it's going to make an acidic solution. So for instance, we have ammonium chloride. So this is a salt, ammonium chloride. Notice the solid. That's going to help you remember that this is a salt. We put that in solution. Please, if you want to do anything good for yourself, write out this equation, okay? Form the ammonium ion and the chloride ion. And I do understand that even writing this equation can be challenging, okay? Then we need to stepwise see, will the anion, the chloride anion, affect the pH of the solution, and will the ammonium ion affect the pH of the solution? Okay. So we're going to take our chloride ion. Again, we're going to imagine reacting it with water. But the only way it can react with water is if it reacts with H+. If it does so, it'll form HCl, which we know is a strong acid. So chloride will not affect the pH of the solution. I'm going to put an X here to say that does not happen. Okay? With ammonium ion, NH4+, hopefully you recognize that this is the conjugate acid of ammonia, a weak base. But in any case, we see it has a positive charge. So it's a cation, so we're going to see how it reacts with OH-. If ammonium reacts with OH-, what do we form? NH3 and H2O. Essentially, yeah. So what we're thinking here now, I guess that's not the best way to think of it for this ion, because this is a weak base, or weak acid. So here we're taking our weak acid. I made a mistake. Thank you. Y'all can just be like, hey lady. Okay, so our H+ is going to come from the ammonium. We saw this reaction before. This forms ammonia, which is a weak base, not a strong base, therefore this happens. And so ammonium will affect the pH of the solution. Check. Okay, so if we're going to work through this, we can write out the equilibrium for ammonia, which we just sort of did. Ammonium ion. See if we'll do it correct. I'll do it correctly this time. Write the Ka. Over NH4+. And then we can calculate the Ka for NH4+, given the Kb, which I haven't apparently put on this slide. Kb for ammonia is 1.8 times 10 to the minus 5. And so our Ka is 5.6 times 10 to the minus 10. Okay. One more thing before we're done. Here's a summary. Salts containing the conjugate acid of a weak base makes an acidic solution. But what if we have a salt that contains the conjugate base of a weak acid and the conjugate acid of a weak base? So for instance, we'll take those two ions that we know affect the pH that we just looked at, ammonium ion and acetate ion. We'll make ammonium acetate salt, and we put that in solution. Here we have our ammonium ion and our acetate ion, okay? I'm not going to work through this entire problem because I think it's sort of beyond what you're going to need to know, but I do want to show you what you can do. So if our salt contains both of these things, okay, here's our conjugate base of the weak acid, here's our conjugate acid of the weak base. Which one will dominate is basically what is being asked. So if we take a salt, okay, hang on y'all, I want to finish this up. And we calculate the Kb value for the weak base, the Ka value for the weak acid, conjugate acid. You'll notice they're the same. That doesn't always happen. This is sort of a freak accident, okay? Okay. What you can do is compare Ka and Kb for these two species, okay? If the Ka is greater, then you're going to have more H3O plus in solution, and so the solution would be acidic. If the Kb is greater, then you're going to have more hydroxide in solution, and the solution would be basic. If you have a freak accident like this, and the Ka and the Kb are equal, what's the pH of the solution going to be? Neutral. But I think that doing actual, my next slide is, relations with that's kind of beyond the scope of the course. Have a great weekend, everyone.